Good evening, everyone, and welcome to the Datathon workshop series. I am Mishka Marzuk, Ambassador of Women in Data Science, Sri Lanka, your host for today's workshop. We are thrilled to have you here as we embark on this exciting journey of learning and discovery. Our workshop series promises to be a valuable learning experience, and we have some exciting guest speakers lined up to share their insights. Before we dive into today's workshop, let me give you a brief overview of what Women in Data Science is. It is an organization with the aim to empower women to reach their full potential in the field of data science. We elevate and celebrate the outstanding work of women on a global scale, fostering respect, collaboration, connection, and visibility. The WITS community creates access to programs, contents, and resources that inspire, educate, and support so that vibrant voices and ideas can be shared with the world. Let me give you a brief introduction to the WITS Global Datathon Challenge. Gilead Sciences is the sponsor for this year's WITS Datathon. The challenge theme for Datathon 2024 is Equity in Healthcare. We are thrilled to announce that it is the 7th annual WITS Datathon competition. Participants are tasked with developing a model to predict if the time for a patient to receive their first treatment for their diagnosis is within 90 days of their metastatic cancer diagnosis. Datathon is designed to help you discover whether disparate treatments and to understand the drivers of those biases such as demographic and societal factors. The primary goal of building these models is to detect relationships between demographics of the patient with the likelihood of getting timely treatment. The first challenge is health inequity, as it has become a global challenge. Addressing this challenge has an extensive positive impact on women's health, which is key for societies and economies to thrive. We have provided a rich worldwide data set which contains treatment, insurance provided, and patients who were diagnosed with breast cancer from the years 2015 to 2018. The timeline of the Datathon Challenge 1 started in January 2024. Entry and team merger deadline is on February 27th, which is next Tuesday. The WITS Datathon Challenge 1 closes and the final submission deadline is on March 1st, 2024. The Datathon Challenge 2 starts on April 9th, 2024. Entry and team merger deadline is on May 30th. The WITS Datathon Challenge 2 closes and the final submission is on June 1st and winners will be announced on the 7th of June 2024. The WITS Datathon is open to individuals. The WITS Datathon is open to individuals or teams of up to 4 members. At least half of each team must be individuals who identify as women. You can connect with global WITS Datathon participants with WITS Datathon Slack, WITS Datathon Kaggle, and WITS Datathon workshops. I welcome you all to be a part of the worldwide challenge Datathon 2024.
Thank you.
Without further ado, let me introduce today's distinguished guest speaker, Ms. Sanduni Jayasundara, Machine Learning Engineer at Octave John Keel's Group. She is an expert in the field of data science. We are honored to have Ms. Sanduni Jayasundara here with us today to share her knowledge and insights on data science and machine learning. If you have any questions, you can send it via chat. Ms. Sanduni, The virtual floor is yours. Please enlighten us with your wisdom and expertise. Over to you, Ms. Sanduni.
Yeah, thank you, Mishka. So, yeah, welcome all. So, today I'm going to talk about the basics of the machine learning as today's session. So, I will share you the screen. And yeah, so as per today, so I'm going to take you through these under these topics. So the first one is understanding what are the data types, and also then I'm going to walk you through how data processing techniques are used for data science projects. And also, that's the next step. I'm going to talk about exploratory data analysis, which is we are shortened and call EDA. It is a crucial step in data science projects. And also, finally, I am going to introduce some of the machine learning algorithms, and I'm going to walk you through in a demo how to identify these data types and data processing techniques, also how to do an EDA, and also how these machine learning techniques can be used for your projects. Yeah. So, first of all, I will talk about what are the data types. So, there are like two major data types. Those are one is quantitative data and one is qualitative data. Here, the quantitative data means the numerical type data that we normally day to day we use like 1, 2, 1, 2, 3 like counting data, and also when like we use everywhere in our day to day life we are using these numerical data for like when we want to, even when we go somewhere we use counting numbers that we have. So, and also the other type is qualitative data, which is called categorical data. In that also we use in our most of the projects we use categorical data. We have like age groups, and also we have like types of maybe what are the maybe vehicles or some other things that we are having in our data set. So those are called categorical data. So what I'm going to do is I'm going to further discuss about what are these data types and how you can understand these data types. So first I will talk about the quantitative data. So what is quantitative data? So quantitative data is a numerical data that also can be break down into two categories. One is discrete, and the other one is continuous. So in discrete category, you may have seen that it is not continuously moving those numbers. Like an example, so when we talk about hiring a staff, we say, okay, we have to hire 2 members for our team, or maybe we have to say maybe 5 members for the team. And we can't say like we need 1.5 machine learning engineer into our team. So that we can't do in some of the cases. So those kind of data points we are described as discrete data points. And also when it comes to continuous, it's like it continues the flow with the data. It has like when we count the numbers from 0 to 1, they're like 0 0.1, 0 0.2, 0 0.3 like data. So in those cases, we say those as continuous data. So in Python, there are like data types, int, double, float, even complex type is there to represent all these quantitative data types. Then I will talk about qualitative data. And what is qualitative data? So qualitative data is the categorical data that also we can break down into two main categories. One is nominal. In nominal category, there are like that can be different things in the same type. So it's like there's no kind of a hierarchy or something. We just can say if you go to a clothing shop, these are like shoe category, these are like blouses, these are pants, like that. But in ordinal category, it's not like that. It has a it's like if we take a like in a company, so we take assistant and managers and trainings like that. So that has a order. So in that case, so the hierarchy is comes from manager director to downwards, maybe, or maybe the trainee to upward as up to director, like that. So in those categories we are categorizing as ordinal data in qualitative data types. So next, I'm going to take you through data preprocessing techniques. So first, I will let you know like what are the main two techniques that we are using to data preprocess. So one main thing is handling missing value. So when we even take a data set, you see in a lot of instances that there are like we can see missing data in the data set. Like for some of the features, we don't have randomly, we don't have data. In some of the cases, we entirely don't have like maybe 2, 3 rows have the data, but most of them are empty like that. And the other method is encoding. This is also a very crucial thing that we have to do the encoding for the categorical variables because most of the machine learning algorithms can't handle string values. So we have to give them a integer value. So we have to convert these categorical or whatever in strings or maybe in Boolean or whatever into a like yes, no, even yes, no categories we have to encode into a number. So that's how we have to feed the machine learning model. So I will first walk you through how to handle missing values. So here, uh, why we get missing values. So in what cases we get missing values. So we can see some of the times like when we enter the data, we don't, okay, so imagine that we have given a form, so we have to enter some data. So in those cases, maybe some people don't enter data, but also sometimes maybe network issues or in some other cases, some of the data won't be properly captured into the systems. So in those cases, we see some of the data points are missing. And also, sometimes people don't want to give sensitive data. So like if we ask in some of the cases, what is the, imagine a bank, that bank is collecting data about the salary of that customer. So they don't want to give that data. And also they ask maybe, if they ask like age, they also don't want to give those data. In those cases, this data goes missing. So we have to have all the, either like we have to remove this data, or either we have to impute this data. So otherwise, like we can't keep empty values and feed into the machine learning system, machine learning algorithm. Therefore, we have to what we have how the values can go missing. So there are like three main ways that values can go missing. So one is MSER, that's called missing completely at random. In this way, the data goes missing, but there's no any dependency with other feature values. So even like so if some value has gone missing, but there are like imagine another 5 features in that data set, like maybe 5 columns. So there's no any dependency missing that data with those 5 columns. So it's like just randomly it's gone missing, something like that. And the other type is missing at random. In this case, these missing values may be dependent of another feature. So it just doesn't go in randomly missing, but sometimes even having a dependency, it can go missing. So this type is that is called MAR. So the other type is missing not at random. So in this case, data has been gone missing, but still there might be a serious issue that why this data has been gone missing. So because we sometimes some of the data, we even like imagine we derive some of the data from some other column, something like that. So we have to investigate why this data has gone missing. If like in some cases, maybe in some surveys, people might not answer. So what kind of questions they haven't answered, and if there's any issue like the question wasn't clear, and why these people hasn't answered, those kind of things we have to like identify why what exactly happened in there. So that kind of data, when that kind of data is missing, we are saying that MNDR, that means missing not at random, that we have to find it, why it has happened, and we have to properly attend to it. So how can we handle these missing values? So there are like 3 ways. we can handle these missing values. Basically, one is we can ignore the missing values. So we don't care about the missing values. Maybe sometimes we can impute some other like 0 or something, and then just omit the missing values and proceed with it. Or else we can drop the missing values. Like when it says missing values, maybe we can drop some of the rows, or maybe we can drop some of the columns that are like missing in those cases. And the third technique is imputation. Imputation means we can, by looking at the other data, or maybe the data in like in the same column, or maybe in the other columns, we can use some methods to generate that data points and keep it. But in that case, we don't delete any of the rows or the columns in that data set. So we have ways that we can do that. Like we can impute maybe mode, median, or mean in from uh, that data column. Also, we can use regression methods, okay, nearest neighbor methods, and we can do multiple imputation to handle those kind of things. And handling missing values, when we ignore the missing values, we can't just ignore because we think that okay, we can ignore this value and then we can't decide. Like we have to uh, properly understand what has happened and how much of a portion in that data has been gone missing. So those kind of things we have to identify. So normally what we do is when we have some missing data, we check how much of a percentage that has been missing. So when it is like maybe under 10%, and it is also it has been missing not under MAR or MNAR, like missing at random or missing not at random, it means it can be gone totally, like missing like completely at random. So in those cases, we can just uh, like ignore those values and then keep the other values and go ahead with the pre-processing. And the other one is, so we can like, we can have to do, so this is the first, like ignore missing values. But then our next one is we can drop the missing values. So when we drop the missing values, when the MS missing completely at random or missing at random are gone in very high, and it can't be like used, because of that case we can't use those column like for the columns for analysis. And also that feature is maybe sample size is more than 5%, then we basically that feature has to be a sample out. Or else in those cases it is advisable to delete the dependent variables to avoid the create the any of the artificial increase of the relationship with the independent variable. So that's why like we are deciding to drop a variable. And also the other technique is case detection. In case detection, um, so in cases which have missing values for one or more features are deleted. So maybe in this case, like through this is an easy approach because we basically decrease the sample size when we proceed this. Also, the data may not always be missing completely at random. So it's maybe most of the time uh, going like missing in missing at random or missing not at random. So this can be lead to biased estimation of parameters when we use the case deletion. And the other one is imputation. So in imputation, the one method is we can use mode, median for numerical values, like numerical columns. So in here, what happens is we try to get the whatever the like we calculate the like the outliers and everything, and get a uh, the max and min values of there, and then calculate whatever the mean or mode and first of all we plot the data and see what we can like use for this. If the the data is skewed and normal distribution, similar to normal distribution, we probably go for median, not mean or mode. So we have to plot and like properly um, study the data set and decide what we are going to do as the imputation. And the next method is regression. So we can use also like regression to generate the data point that has been gone missing. So basically what happens here is we can use independent variables and fit it into equation that can generate the dependent variable where the missing values are there. So in that case, we can predict the missing data points by using regression methods. So the other one is k nearest imputation. So what happens here is we have, so as the k nearest neighbor algorithm, what happens is we measure the distances from the chosen so neighbors, and then what we do is we estimate the both qualitative attribute, what has like frequently what is the nearest neighbor that has been frequently like dropped in those features, whatever the other features are available. So in those cases we get the nearest neighbor and we assign that neighbor that data point to that neighbor which is the nearest neighbor. And the last one is multiple imputation. In here, what happens is in what we draw the distribution and then simulating the random draws, and it doesn't include uncertainty in the model parameters. Some one of the approach we use to do multiple imputation is Markov chain Monte Carlo simulation, and here the step of the result is complete data sets, and we analyze those data set, each of the completed data set, and then we use the pooling to integrate the M analysis results into the result. So that's what basically when we basically what we use to when we do the imputation. Then I will take you through the encoding categorical variables. So basically this, we use this for categorical columns. So there are like several techniques that we can use for when we try to encode the categorical variables. So first one is one-hot encoding, and the other one is binary encoding. The other one is frequency encoding, and also label encoding and ordinal encoding. And as I mentioned earlier, we need to encode categorical data because ML algorithm does not support categorical data. It has to be fed as a numerical data. So why we use encoding technique to handle that. So in one-hot encoding, what happens here is we have like several classes, like we have as shown in this example. So we have red, yellow, green, and again yellow, like those kind of several classes. So what we do is we generate one more column like for each and every class. So if it is red, then we create another red column. And now when we create that column, we assign one for that in that column where the red was there. So as shown in here, so you can see when it's in this column, red is there. So when we generate the other column in one-hot encoding, what we do is we assign one for those two rows, and then we put the 0 for other rows which are not having reds. So like that. So it's same for the yellow. So you can see, so the yellow is here, and then you have the yellow column, and where the two rows where the yellow is there, we put 1, and then the other columns will be 0. So when the value is absent in that column, we put 0, and when the value is available present in that column, we put 1. So that's basically the one-hot encoding. Next one is binary encoding. So what happens here is we convert some class into a binary digit. So how we do is we have, so in here as shown in here, we have temperature as hot, cold, and very hot, and also warm. that's also there. So what we do is, so we have an order. So for each and every class, we give an order first. And so in here, when it is hot, we have given 1. And when it's cold, we have given 2. And when it's very hot, 3. And warm, 4. So we have 4 main categories. And it has been now assigned, like all the 4 categories has been assigned into an order. So when these categories are repeating, we are assigning the same order number for that relevant class. And after, when we have the order, we convert into a binary code. So as you can see, this is the related binary code for order 1. So in like that way, once we generate the binary codes, so we have all for all these um, classes, we have now binary codes. So then we similarly we did for the one-hot encoding, we create several other columns and then put those order numbers. According to that order numbers, we put the 0, 1, whether it's present or not. So if we check here, you can see when it is, so we have like, since there's 4, we have 0, 0, 1. So this 1 is present here. So we have the coding as temperature 0, temperature 1, temperature 2. So these 2 goes to these 2 columns, the first 2 in the binary, and then the last 1 is go to the third column. So same way it goes like to the bottom. So if you see the last one, so when it is 0, 1, 0, then the temperature 0, the first column will be the first digit in here. And then the second one is the second digit in here. And then third one is the third digit in here. So that is how the binary encoding is happening. And then the next one is frequency encoding. So in frequency encoding, what happens is we have some data set and these classes being repeated in like, assume that n times, and we have m data points. In that case, what happens is we give a value, like how many times it has been like, it's called like based on like their relative frequency. So from out of all the out of all the data point, how much times exactly one data point has been repeated. So in this case, we have assumed that there are like 9 data points are there, and now out of those 9 data points, A has been repeated 4 times. So when we then the value will be 4/9. So that value will be encoded in the encoded feature here. So same as same in for the B also. So B has been repeated 3 times. Then we get the relative frequency 0.33, and it will be added here. Like that way, for the C, the same calculation will be done. So that's how the frequency encoding will be done. Now, we will see how the label encoding will happen. So we use label encoding when numerical values are so in label encoding, what happens is there will be some classes, and we will assign some numerical value for that classes. Basically, it will be a unique integer, like shown here. This will be the original data. Here we have A, B, and C. So basically, what happened is we start from 0. So for the class A, it has been assigned as 0. And for the class B, when the class changes, when class B comes, it's assigned in the next integer value. And when the class C becomes, when it has been assigned the next integer, which is 2. So it's not that complicated way. So basically, what basic way is just you have classes. Whenever the class changes, it will be assigned an integer for representation. Basically, class will be converted into an integer representation. Yeah. So the um, the last encoding method is ordinal encoding. So here what happens is we assign each unique value to a different integer. So here you can see every day, never, rarely, most days, and never. So what happens here is for each and every this category we assign a integer value is same as the label. It's similar as the label encoding. So we what we do is like we have like when it's every day, it's zero, 3. So it's like never, it means 0. So it has a meaning of it. So we have never means that will never happen. So therefore we put 0. Really means that might be happen, but it's not maybe most of the days. So therefore we put as 1 in there. But when we come to most of the days, that doesn't mean that it happens every day. So it will be 2. So every day is 3. So it basically give the weight, that means the high integer value according to the meaning of that. So that's how we do the ordinal encoding. Um, Now we will see what is exploratory data analysis. So that's basically we normally call as EDA. So here we have like several steps that we do exploratory data analysis. So once we figure out what kind of data available and also how the behavior of the data is happening in the data set and what we have to do before we feed the data set in the machine learning model that we explore in this exploratory data analysis. So here, as shown in here, so basically key features of this exploratory data analysis is to uncover underlying patterns in the data, and also we check whether how the data set structure is been here, and like the data types and what kind of whether the data is categorical or maybe whether it's in like numerical, and also what kind of anomalies and what kind of data has been gone missing, and what kind of relationships we can see in between the features like means independent variables and dependent variables. So all these things will be explored in this EDA part. So basically the first step in EDA is loading the data. So what we do is like data will be available. Data is available like in different formats. So basically in different databases we have to collect. So that's the first step in the EDA. We collect those data which is related for which we are going to use for our machine learning model. That is the first step. And then we check for like summary statistic like how the means are there like mean they are in the for the numerical variables, and how the medians are there, and how the sorry no how what are the max values and mean values. All those things will be checked in here. So we have like some functions just to like check. So we can use some pandas functions maybe and check these or the summary of statistics for about your data set by using that. And also in EDA we use dimensionality reduction. So what dimensionality reduction is, sometimes we get data set, it has like maybe thousands of features. So in these cases, what we want to do is we want to reduce the sum of the variables, but we don't want to um, harm the original the information that was there in the data set. So what we do is we use techniques like principal component analysis or maybe T-distributors or Catis-Newber embeddings to reduce this high dimension data into maybe smaller dimension of data, so that we can use this data for machine learning algorithm to give it like predictions in efficient way. So that's what basically dimension reduction is used for. And also this dimensional reduction techniques being used for the huge data sets. Like when the data is load is a lot, we use this kind of data because it's easy to handle after. Um, then once we figure out what kind of a data set we have and what we have to do, then we do the data preparation. So in data preparation, what we basically do is we have to transform some of the data, like maybe like integer data into maybe some other type of data. Also, maybe we have to aggregate some of these, or maybe we have to like do, if it is like transaction data, we may have to get if we have in daily level transactions, maybe we have to get weekly level transactions. So in those cases we have to do those kind of aggregation calculations, and we have to clean the data, like when there's like uh, anomaly data kind of we can identify like anomaly data. So maybe imagine like it should be a transaction, so it should be some integer amount, but also sometimes some system errors or something happens, and then there will be some strings or unknown characters might be there, and also some missing values are there. So those kind, and also there are like sometimes there are like lot of duplicates are happening in our data sets. So those kind of things has to be ignored before we fed the machine, uh, before we feed the data set in the machine learning model. So this step, what we do is basically we handle all those issues and clean the data set. And then also we can visualize the data and see how the relationships are there within the like between the features, and how the relationships are like. That means we can see what features are affecting to each other, and also we can see which kind of features are like affecting to the dependent variable, like what has the highest effect to the dependent variable. Those kind of things we can have some plots, and we can see these complex trends and relationships through those easily. uh, so the other one is in the EDA we perform variable analysis. So basically we what we do is they are like we have to get insight for these insight for the correlations of the variables that are in the data sets. In those cases, so we have like three techniques we can do this. So one is univariate. So here we examine each variable within the data set on its own. So in this scenario, we can uncover the insights such as median, mode, maximum, range, and outliers. And the other technique is bivariate. So here, what we do is we reveal the insights between two chosen variables. So the basically we use two variables and focus understanding the relationships and distribution, how it happens between these two variables. So the first one is within only that specific variable, but in the second one, the bivariate one, so we use two variables and then check the relationship in between those two. And the third one is the multivariate one. So here we use like a set of statistical technique for used for analysis of this data for that involves multiple variables for observations. And this approach is very critical in understanding when it comes to complex relationships among the several variables simultaneously. That means, so it means like we have maybe imagine 10 variables. So we want to see how these every variable behaves with maybe two or three, like what kind of variables has, so like maybe a dependency with another two variables, those kind of complex relationship. So to identify those kind of complex relationship, we use multivariate method. So next one is the analyzing time series data, but this doesn't happen all the time because sometimes in our data set there might not be time series trends will be not there. So to have a time series trend, you should have data that has been changed over a time. So basically some of the cases we don't, if we don't have any way to capture that, okay, there's been a time that data has been collected also, we can't do the analysis for this time series kind of data. So the focus of this time series analysis is to check the trends between the data in a regular intervals like years, maybe months, and maybe weeks, and like that. So this method is very crucial when it comes to maybe the industry data like transactions in some sectors, like those kind of cases. So sometimes we want to see how the sales has been happened in last 3 weeks, maybe last 3 months, like that. So this analysis is very helpful before we go and use some like machine learning algorithm and predict, because we imagine that we don't have any idea how the data is behaving. Maybe if we, like as an example, so as you all know, so we had this COVID situation in the past. So in those cases, if we don't have an idea that in those cases only the sales has gone down, and we just feed the data into the model and then get output, maybe that output will be not accurate because that there was a like specific reason for that duration. So those kind of things we can identify by time series analysis. Then the other one is hypothesis testing. So this also we sometimes doesn't do hypothesis testing exactly, but most of the cases we do because it's crucial when we want to find the like type 2 error or type 1 error. And also we can check the relationship between variables very efficiently here, and it helps to determine the pattern of the data that how the significantly it has been occurred in any chance. So that we can get any idea, that we can get the idea from here in those cases. So therefore sometimes we do the hypothesis testing as well inside the ETA. So next, I will give you a brief introduction to basic machine learning algorithms. So here, I am going to first discuss about the regression, and I am going to explain what is regression. So in regression, what happens is it's a basically statistical process. So what we have is we have a dependent variable, and there are independent variables. So we predict, so what we generate a equation that this equation can predict when we feed the independent variables into that equation. So it will predict the what would be the independent variable. So that is the basic idea, and this is most of the time we used these regressions for integer type like behavior data, like linear regression like things. But there are like some regression models even we use for classification kind of things also. So it's the best example is logistic regression. So basically in regression what happens is you have given a response for this model, and then it will predict the outcome of it. As an example, when you want to predict a housing price or something, so you give the maybe dimensions of the house and how many bedrooms and how many bathrooms and everything, and then it will predict, okay, this should be the price for your house, something like that. So those kind of cases we use regression models to predict. So the other method is classification. Here basically there are like main two categories. One is binary classifier and the other one is multi-class classifier. So in classification, what happens is we classify like data into a classes like when it has the same behavior of that data, we classify it as a like it is belong to this class, something like that. So basically what happens here is in binary classifier, you have yes or no or male or female, say spam or not spam, like that. So you have only two classes. When you have two classes to predict, we use binary classifiers. It called as binary classifier basically. So if we have like more classes, more than two, like those cases we use multi-class classifiers. So maybe in those cases, like maybe you want to predict the age group of a person by giving some other height, weight, or maybe uh, some of his eating behaviors or something. Then you want to predict, okay, this person must be in maybe 30 to 40 age group, something like that. So you have several classes. So in those scenarios, we tell that it's a multi-class classifier. Um, yeah, so that is basically the classification. What is classification? And then the next one is clustering. So here, what happens is, so basically classification, we train with example data. So in clustering, we don't have label data. So in classification, we have label data. So it's been labeled, okay. So when it is a spam email, so when we train, we label it whether it's spam or not. So we specifically know we are going to predict a spam or not. So like that. But in clustering, what we do is we use unlabeled examples to make them into a clusters. So this is kind of a unsupervised learning technique. Uh, and it has the one of the biggest advantage it has is it can cluster over a supervised learning, like even the classification as well. So in here, like we have several techniques, like we can use k-means or mean shift, db scan or hierarchical clustering, like that, those methods to do the clustering. So yeah, so those are the main algorithms that I'm going to like discuss. And then now I will take you through the demo. So I have used this medical data set for you to see how it's been. Let me share the screen. Yeah. So hope everyone has configured the collab panel. Is there anyone who's facing issues with that? Okay, I hope everyone is fine. So I will give a brief introduction about the data set. So here I have used the Kaggle data set, which has predicted which has to be predicted stroke, whether the person has stroke or not. So in this data set, we have like 12 attributes. So here the first one is a unique identifier, which is called ID. And the gender column is there, and it has values as male, female, or other. And the also we have the age column as well. It's basically the age of the person. And the fourth column is hypertension. So if the patient does not have hypertension, it will be 0, and if the patient has the hypertension, it will be 1. And also the other column is heart disease. That also, when a person has a disease, it is 1, and when the person doesn't have a heart disease, it's 0. And the other one is they have captured that whether the person is ever married or not. So it's basically a yes no like label. And the seventh column is work type. There we have category, like it's a categorical column where we have the values children, government job, or never asked, private or self-employed. And the other column is residence type. It is has rural or urban in that column. And the ninth column has average glucose level. Sorry. So basically, it shows the average glucose level in the blood of the patient. And the 10th column is BMI. So in that column we have body mass index captured. And the 11th column has smoking status, where the status has categorized as formerly smoked, never smoked, smokes, or unknown. And the last one is stroke, whether this patient has a stroke and then he has a stroke or has not having a stroke. So if he had a stroke, it's 1, and if he is not, then 0. So I have mount in here. I have mount the um, data set from my Google Drive. I hope you all know how to mount the data set and get the data set from the Google Drive. So after that, I have import the libraries. So basically, I have used NumPy, Pandas, and Seaborn for Matplotlib for visualization. And also I have used for the pre-processing from the scalar, robust scalar, label encode, and min-max scalar. And from the model selection, I have used the functions like trends, like splitting trend and test data set, and cross-validation and grid size CV. And also from the metrics, I have imported accuracy score, classification report, and confusion metrics. As model, from the linear models, I have used a logistic regression because this is a classification data set. So what we're going to do is to predict whether the person has has a stroke or not. So therefore, I used logistic regression also, and also k-neighbors classifier also I have used, and random forest classifier, gradient posting classifier, SVC classifier, also decision trees. These all the classifiers I have used to generate the model and show you how the like predictions are being given from each of these classifiers. And I have also used the sampling technique called SMOT. So I will explain it while I'm going through the code. So, and also I'll show you how when the sampling is done, how the models are behaving, whether it's increasing the accuracy or decreasing the accuracy, or that also I'll explain. Yeah, so here I have read the data set as pandas data frame. So you can see data here. So as I mentioned earlier, so these are the data columns you can see. And so in here you can see the ID column and gender, male, female, and age is given, and these hypertension, heart disease, and all these are like, some of these are categorical you can see, and some of these are numerical, and you can see as in BMI you can see here some null values are there which call NaN. So yeah. Yeah, I think everyone is clear up to this point. And now we will see how the data set size is, and also we know that we have uh, 12 attributes like the columns. And we have here, when we use the data frame name is stock data. I have read as a data frame using pandas. So here the shape is we have 5,110 data rows and we have 12 columns. So you can get that from by using data frame dot shape. And then if you want to see what are the columns again, then you can use simply stroke dot columns. So it will show you the data columns. And if you want to see interactively, like how the data points has been shown, like here you can see it's just the data frame. So if you give data frame dot head and a 10, you can see the first 10 data points in that data frame. So here you can see the data frame first 10 data points here. So by using this command. And then once you use data frame.info, you can see the details about the data, like the columns in the data set. You can see the ID has data type of integer 64, and you have for the age it float because it has some of the decimal numbers. And also this ever married work type and all this has been identified as an object type, which is because it was like categorical data. And even smoking status. So here you can get an understanding how the data has been identified when we load the data set to the data frame. Yeah. So now we will do the exploratory data analysis before we do the pre-processing. So then we can identify like which data has anomalies, missing values, and outliers, those kind of things before we do the pre-processing. So we can do the data pre-processing one go. So here, basically, as the first step, what I did was I got the count of the null values for each of the columns in the data set. So here, when you run this, you can see that only BMI has null values. It is 201 null value points are there for the BMI column, and others don't have any null values. So what I did was then calculated it as like the missing values as a percentage. So it's basically 3.93% of the uh, data set that has BMI values are null. So that's what happened. So that's how much the 201 missing values are in the data set. It's basically nearly 4% of the data set. And then what I did was I plotted also into a graph. So you can see, so this is the missing amount. So graphically, what I did was I first created a missing data count for the BMI missing and BMI not missing. And then I plotted into a graph to see how much is missing and how much is not missing in a visual manner. And after that, what I did was I checked how the categorical and numerical variables can, like how those are present in the data set in the columns, like which columns are categorical and which columns are variable. Here I have created a function. Basically what I have done in this function is I am getting the column names that has integer 64 and float 64 types um, as a list. And for that is this is for sorry, numerical. This is for, oh yeah, this is for numerical. So this one is enough. Yeah, this one is enough. I have repeated, my bad. Yeah. So I got the category numerical type, and then yeah, yeah. So this one, let's remove it. And then there are some numerical values, but also those are like categorical. Like, so there, what happens is, so how I identified those was when you have, uh, so there's a function called n unique. So what I have done is this n unique may be having, like, imagine that some of the cases we had columns, it mentioned like 0 and 1, like, so in those cases, this also categorized as a categorical variable as well. So what I did was, if there's a unique values below 10, so I counted it as a numerical, it has been identified as a numerical column, but it should be a categorical variable because it has a like Boolean values kind of, or maybe if we have like maybe three date like three classes kind of, that also we can identify it as a numerical. So in those cases what I did was I got those columns as also from the numerical into categorical variables. So here that I have given a filter that when the unique numbers are below 10, it should be a categorical variable, it, though it has been captured as numerical. So, and I am adding those into a categorical column. And then after that, when I have uh, some of the so there are some numerical columns, those are like, those are categories. So we have to remove those numerical columns from the numerical like list we have calculated earlier. So, and I have removed those as well. And after that, what I have done was I have taken all the numerical columns and categorical columns into a separate two variables. And for the numerical columns, we have like ID, age, average level, and BMI. So if we go and see here, so age here, and so these are basically shows as numerical, but these should go as categorical values, categorical column. That's why I mentioned like some of the columns which are go as categorical has been identified as numerical because it has numerical values in this column. And also these are numerical, and these are numerical, and these are categorical. So if we go and see, so we have categorical columns and as hypertension, heart disease, stroke, gender, these ever married, those columns has been now identified as categorical column. And these are the ones that was identified earlier as numerical, but those were categorical columns. So as I mentioned like that. So here the Boolean kind of values. Yeah. Uh, yeah. So now, oh sorry, got it. What is uh, categorical? This yes, okay. And now here what I have done is I have now analyzed, so where I have here I have analyzed the numerical attributes. So basically now we know the columns which has numerical attributes separately and columns which has categorical attributes separately. So in this step, what I have done is I have I am going to analyze that all the numerical values. So basically for the categorical values, we can't get this kind of a description because those are like categorical values. So here for these numerical columns, what I have done is I have used the describe function to see how the these how many records are there, and this is basically the shape of the data frame, mean and standard deviation of that column, min of that column, max of that column, and how are the interquartile percentages has been they are in these columns. So that is what basically this describe function does. And after, what I have done is I have plot these graphs for each and every so each for each and every numerical column I have plot this graph for, like, we can see here for the ID, it's just basically just the ID column. We specifically doesn't need this for training or anything. And the crucial ones are age like column. So here you can see most of the in the data set, like you can see in the middle of the data set, there are like lot of records are there for the age. But in for the glucose levels, you can see most of the most of the records are there for the glucose level between maybe 75 to maybe 125, like. So in this range, most of the glucose levels records are being present in the data set. And when we check the BMI, you can see that BMI is basically a kind of skewed and normal distribution. The like average kind of goes in between maybe 30s. So this is how the BMI data present in the data set. So yeah. And in the next step, what I did was I checked the outliers. So I used for the numerical columns. So I used box plot for this, where it is very easy to identify the outliers by using a box plot. So here, what basically I have done here, the ID column doesn't matter. But for the age, we can see like there's no specific outliers for the age. But when we come to average glucose level, you can see like a lot of outliers here. So these are the interquartile ranges. So apart from that, there are like a lot of outliers you can see present in here. And also same, it's same in the BMI. You can see like a lot of outliers in BMI as well. Yeah. And so here, what I have done is by this, I have calculated the interquartile now, like values for like upper limit and lower limit. And then I have checked whether when we give a data frame with the columns that we want to check, whether those numerical columns have outliers or not. So this will return the columns that has an outlier, basically. So here you can see when I call the function with the data frame and then the set of numerical columns, you can, I will run it. And then outlier calls. So you can see BMI has a lot of outliers here. So it has, in the function, it has been identified. So if there's no outliers, it will print there's as there's no outliers. So after that, I analyze the categorical attributes as well. So here I plot each and every for each and every categorical variable. I plot a graph here. So here what you can see is for the hypertension, there are like more than 4,000 plus is no hypertension, but like there are like 500 or maybe in between 400 to 500, there are like hypertension is present, and heart disease is present for like a lot of it, and in the data set. And you can see like in these two graphs, like when the heart disease is there, even then the heart stroke is like similar behavior in those data columns. And when it comes to gender, there are like a lot of males in this data set, and also most of them are married ones, and also maybe half of it not married people. And when it comes to work type, most of these people in the data set are private sector, and like there are few children too, and also never worked is very less, and maybe self-employed and government jobs are like in between, like and then the next column was resident type. So there's no like basically much difference in the resident type. You can see like nearly falling the same kind of amount of the data in the for the resident type. And smoking, when it comes to smoking status, you can see like formerly smoked people are very much in the data set, and never smoked also there. And also smokes is less, and unknowns also available in the data set. So that's how the categorical columns behavior in the compared to the total count of the data set has been captured. And now what I have done is I have analyzed the target variable, which is the stroke. So here what I did was I counted the target variables, like I got a value count where the stroke is 0 and 1, and I plot it into a graph. So here you can see the 0 is a very limited amount of strokes. You can see it's a biased data set, like the where the class sample 1 is very high in this data set. So as a percentage, it's a 95%, 95%, 91.5%, 95.1 is which they had strokes, and 4.9 which they haven't got the strokes in the data set. And then I check the correlation between the columns of the data set. So basically here I did the correlation between the numerical data. So here you can see there's no much correlation between the each and every numerical column, but kind of correlation we can see for as 0.33, which was the maximum for this, for the BMI. So that's it. So others are like basically very less for the other categories, so they don't have much correlation between. So after that, what I did was I checked the target variable with numerical attributes. So here basically what I did was I grouped by the stroke, where the all of those numerical columns. So for the ID, age, and BMI and average glucose level, I check how much therefore like where the stroke is present and where the stroke is not present, like as the mean. So here you can see here, so the BMI so this ID we just doesn't check in because it's just the ID. For the age, you can see the stroke is 0 for like the average is 41.9. So the people in those average, they won't get the stroke. But when it comes to like 67 ages, so you can see it's the average is like that for the stroke is present. So also for the glucose level, you can see when there's no much glucose level for the people who doesn't have a stroke, but the glucose level is very high for the people who had a stroke. Also BMI is also the same. So these all are like high for the people who had strokes, but it's less for the people who didn't have strokes. So, and then I checked with the categorical variables. Here, so in here, you can see that for the hypertension, mean is 0.03, and for not having a stroke, and 0. No, sorry. So hypertension is 0. That is when hypertension is 0, it's like 0.02. So there are no much people in this where the hypertension is 0, but it's more than that when it comes to the hypertension is there. So it's increasing. Like the stroke, the people who had strokes are a lot when there is a hypertension. And even in the heart disease case, you can see compared to the stroke, they have a heart disease, it's more frequently to have a stroke. And for the gender wise, for the females, it's lesser, but for the males, it's a bit high that they have a stroke. Also, married people also it's high for them. Not for not like there was not much for ever married. So yeah, and also you have this. You can see this for the job-wise worker type. They are also the self-employed people have the highest target mean. So you can see here, when it's like they are self-employed, they highly likely to get a stroke. And also when they are like in urban areas, they highly likely to get a stroke. Also when they like formally smoke, also they are highly likely to get a stroke. So yeah, so according to like this, all the whole EDA, so what we have now found is, so people with hypertension are more likely to have a stroke. Also, people with heart disease are more likely to have a stroke too. So, and probability of having a stroke is actually more than having a stroke by females. You can see here. And also people who have been married are more likely to have a stroke than people who weren't married. And also people who are self-employed also have more likely to have a stroke. Those are like the findings, like also so in urban and also in people who formerly smoked, also they have high probability to get a stroke according to this data set. So those are the findings basically we can see in this data set by doing the EDA. So once now we know like BMI has outliers, and we know that some of these categorical variables are highly giving insights about how much of strokes can be happen according to their way, like how when these categories are like deviating, like with differentiating to each other. So in that case now, like we know we have to focus up the categorical variables, and also we have to clean out the BMI values. So as the first step, what I did was I checked for the duplicate values. So here we didn't have any duplicate values. This is basically the part of data pre-processing. It also called as feature engineering. Here after, so since we don't have duplicate values, so now we can fill up the missing values. So here I used the median to fill the missing values in the BMI. So because as you can see here, so when we use median, because this is normal distribution and skewed, it doesn't affect much of a outlier problem when we use median. So unlike the mean, so that's why I have used median here. So you can replace the null values from data set by using median in the BMI column. So, and then I used a label encoder for the columns which had unique values and unique values for two. That means 0, 1. When we have to 0, 1, I used a label encoder to encode those. So here you can see I got the columns that we have binary data. Sorry, this is not 0 and 1. This is yes or no, or resident type, urban or rural. So these are like string values I have got it from. And then when we have it, you can see the binary columns which we have two variables, and those are categorical. Those kind of column, like those kind of data columns, we can see like two are there. One is ever married and resident type. After that, I create the label encoder class, and then I added the label encoder into the data set. So here what happens is for each and every column in this binary column variable, I will fit this label encoder transform for that column. So once I did that, here, so we did it for ever married and resident type. So yeah, you can see here, ever married is 111 and resident type 1010. So yeah. So now the two columns that had categorical variables, we cleaned it. And then now we are going to apply one-hot encoding method for the variables which has that unique values more than 2 and less than 10. So basically we don't have in unique values 10 in the data set. So I just use that. We just only use even more than 2 as well. So what I have done here is basically when you have like categories more than 2, then I will be using one-hot encoder that I explained earlier to make the data set into a numerical, like those data into a numerical column. So here I run this, and here I am using this get dummies function to make the columns. And then now the one-hot encoding has been applied to the data set. So when you run this and see, we applied for gender and gender. So you can see here. So here gender male, it has been created the name as gender column name and the category name, and gender other, like that. Also for the other gender other, okay. And for the work type as well, so the next column is work type. So never worked, private, also self-employed, and also with children, someone that's also been added to the data set as according to the one-hot encoding. And smoking status also has converted into one-hot encoding columns. So here you can see. So now dataset has all the numerical values, but still we have to deal with the outliers, and we have to bring the sum of the values into we have to check the min max values and then bring those values in between to make the algorithm predict more efficiently. So here I have used interquartile range method to get their upper and lower boundary limits and replace those by the outliers by those limits. So what I have done here is basically I have defined a lower threshold and also up threshold as 0.1 and 0.9. And after that, I am calculating the interquartile uh, after calculating those threshold. And then I'm calculating the upper limit. And once I calculate the upper limit, then I am assigning whatever the data points which has gone above that. So when it is lower the limit than the low limit, I have assigned the low limit for that data point. When it's the up limit is more than the up limit, like the upper, whatever the data point is higher than the up limit, so I am assigning the up limit for that. So basically then the data, all data will be within the low limit and the up limit. So that way I have handled the outliers. So then I am replacing those outliers. And after I replace the outlier, then I am calling the function that I used earlier to check the outliers. So for the same data frame, the numerical columns, now you can see it's printing, there's no outliers. So now we don't have any outlier columns also. So now we can do the feature scaling. So we use feature scaling in cases like here you can see in this data set, we have zeros, ones, but we have like 228.69, 36, like these are like very much of a variation with when we think about the values, like these are very small and these are kind of like very big values. So what we do is we will bring those into a similar scale, so that is called the feature scaling. So here what I have done is I have used min-max scaler. So by using min-max scaler, we can bring these some of these values which has higher values, like here you can see glucose level, BMI, and also here the age. So I got those, and then I use the fit transform by using min-max scaler. And then after scaling out, you can see here, so the age has been now like in a scale, not like a higher scale, even the glucose level and BMI. So now it's kind of a clean data set. So now I think our data set is ready to train, like to feed into a machine learning model. So up to here, what we have done is just prepare the data set in a way that we can feed the data set into a model. And now what we can do is now we can do the model building. So here I have defined the y variable, which is a dependent variable as stroke, and independent variables are the variables apart from stroke and ID. So I have dropped those columns. So that will be the X. And I have used logistic regression, k-neighbors classifiers, decision tree classifiers, random forest classifier, also support vector machine, XGB classifier, LGM classifier. These all are like classification algorithms. Like I have given a brief description here. Also how these basically these classifications are working. So you can have a look there too. And I am here assigning a list of models named as a variable called models, that so that I can use one function that iterate through this list and then create the model, like train the model and give the accuracy levels. So this is the list for the models, and now I am iterating through the models, and I am using cross validates and regressor in here in the models, and then using CV5 and scoring methods, I am using accuracy, F1, recall, and precision. And then I will print those accuracies after training. So here, so yeah, so here you can see for the linear regression, accuracy is 0.95, k nearest neighbors also 0.95, decision tree it's less than that, and random forest is 9.4, SVC is 9.5, and you can see like how the accuracy is being there for the predicted models. So now what I will do is, so as you saw here, so if we go to top, so here, so we are going to predict stroke where we have like a little amount of zero strokes and then a high amount of which people had stroke. So this is calling this is a minor sample, and this is a minority sample, and this is the sample which has a lot of data, and this is the which is called minority sample, which sample that doesn't have much data. So this is not balanced two classes. So as you can see, like we have 95% one for having a stroke and 4.94 not having a stroke. So basically this is a imbalance class data set. So now I did the training and everything for the imbalance class. What now I'm going to do is to use SMOT to use a balance sample. So where I can generate some of the data by the method called SMOT. So in synthetic minority of oversample technique, the SMOT means. And then here, what SMOT is doing is, so you have minority class, it will generate some of the random example from the minority class, and then it will generate the k nearest neighbors for those examples. Like basically we normally take the k as 5, and then it will randomly select those neighbors and chosen in the synthetic sample and generate more those two samples into a balance sample. So basically it will increase the minority sample by generating more same kind of similar data points in that class, same class. So here before using minority, before using SMOT, so I will show you. So here why train where the one is before using like SMOT method. So you can see it's just 189 records are there for one, and here you can see there are like 3,900 for 0. So you can see the minority class is here 189, and then when we so we use this is the X-Trends mod, Y-Trends mod. This is we are using resampling technique to generate data for the X-Trend and Y-Trend, which we were using earlier, like here, to generate this data. So this data. So by using those, we use those two like the data points like the X and Y, and then create a separate train X train and X test and Y train and Y test. And from that, we are using these X-train and Y-train to generate more balanced X-trains mod, that is the variable name, and Y-trains mod, which has the balanced data set. So when I feed it to this, so now we will see for the Y-trains mod, it's now when it's equal 3,899. So you can see like it was earlier 1,189. Now it's now increased. Like we have a balanced data set now. So once we use the smart. So now we train the data set again using these data like the Y and X variables. So here, now you can see the accuracy has been increased. Like it was 0.95 earlier, like that. So for the linear regression, its precision is 0.98. So it's everywhere it's been now increased. This is the confusion matrix, by the way. So yeah. Yeah, I think that's the end of the demo. If you have any questions, you can go ahead. I think that's about if there's no any questions.